Okay, let's get started. So yesterday we have seen yet another sorting algorithm, which was heap sort. So this means that so far we have considered three types of sorting algorithms. First one was insertion, second one was merge sort, and finally we have talked about heap sort. Remember that for insertion sort, the running time, we made two separate analyses of running time. One was the worst case. In the worst case, it could be the case that insertion sort requires theta n square running time. However, in the best case, we know that the insertion sort algorithm requires linear time, theta n time. For merge sort, for the second type of algorithm, we didn't have such different analysis. All the time, the running time of the merge sort algorithm was theta n log n. And finally, the heap sort algorithm that we have seen last week and yesterday required again theta n log n running time. Today we will talk about quick sort, which is again based on kind of an incremental idea or based on divide and conquer. Remember that merge sort was also based on divide and conquer. Let's review the main idea in merge sort. We were saying that the input into two halves, A1 and A2, and recursively let's solve the problem for A1, which means that we call merge sort on this A1, the smaller array, and also call merge sort on A2, and then the next thing to do would be to merge those two sorted arrays, A1 and A2, back into the array A. Okay? And most of the time, to do the division, actually we didn't do anything special. Computed a middle index to find out where to divide the given input array. Most of the running time that we spent was actually for the merge operation, okay, which was theta n running time, the merge operation. For quick sort, but note one thing, that the merge sort algorithm is not in place, meaning that it doesn't do the sorting operation on the given input array itself. It needs some extra space for storage. Why was this necessary? Remember that if this is A, we split it into two, we make a copy of this left array into a new array A1. And the same is true for the right part. We make a copy of this right subarray into a new array A2, and then solve the problem for A1 separately, solve the problem for A2 separately, and then while merging, we can use our original array. So merge sort requires some extra space for storage. It's not in place. We will see another algorithm which will be based on divide and conquer as well, the quicksort algorithm, and this time this algorithm will be an in-place algorithm, meaning that it will do all the sorting, all the operations, all the assignments and so on will happen on the given inputs array. Let me first ask a question. So do you think that the last sorting algorithm, basically heap sort algorithm, is it an in-place algorithm or is it a not in place sorting algorithm? Anybody has any guesses? The heap sort algorithm that we have seen starting last week, and we have also seen some analysis regarding heap sort yesterday. Is heap sort an in-place sorting algorithm or not? Any ideas? Can everybody still hear me, by the way? Okay, so Faizenur makes a guess that it is in place. Emir also says that it is in place. That's true. Heap sort is an in-place algorithm, because remember that we represent the given heap as an array. Okay, and remember the main operations of the heap sort algorithm. When we are given the input array, we call build heap on the given input array, and for the build heap, we repeatedly make calls to heapify algorithm. And heapify actually does all of its swap operations on the given input array. So everything, all the swaps that are necessary throughout the algorithm itself are all in place. Let's now start with the new sorting algorithm, quicksort. For quicksort, it will also be based on divide and conquer. However, just the opposite of merge sort, this time we will do most of the job required for sorting in the divide step. Remember that for the merge sort in the divide step, we didn't do much. We just computed a middle index. For the quick sort, the divide part will require most of the time, will require most of the running time that is needed by the quick sort algorithm. Once we do the division according to certain property, which I will describe in a few seconds, we recursively solve the problem for two smaller parts, for the left subarray, right subarray, and finally we will merge the results. Remember, for the merge sort, most of the time was spent in the merge part. We will see that for the quick sort, we will do the division in such a way that when the time comes to merge the solutions, we will almost spend no time to do the actual merging. Okay. So the most important part for the quicksort algorithm will be how we will partition or how we will divide the given input array. This will be the main property that we will want from a partition algorithm, from the algorithm that will divide the array into two subarrays. The algorithm for partition will make sure that an element that exists in the original array, let's call it the pivot, will be in its correct position. So let's say this is 1, 2, 3, 4, 5. The fifth smallest element in the whole array, if it is the pivot, will be at index 5, will be at its correct position. This is one property. So the pivot element must be placed into its correct position in the array. And the second important property that we want from the partition algorithm is that all the elements that are less than or equal to this pivot element should be placed to the left of it in the array. It doesn't matter how they are organized within themselves, but anything that is less than or equal to pivot should be placed to the left of the pivot, and anything that is greater than the pivot should be placed to the right of it in the array. Okay, so these are the two properties that we want. One of them, pivot must be at its correct position, and the second one is all elements smaller than or equal to it are to the left of it in the array, and all elements to the right of it are greater than it in the array. If we can achieve to do this, if we can achieve to solve this partition problem, okay, you should be able to see that then sorting the whole array is quite easy. How? Because since we know that all the elements less than or equal to pivot are placed to the left of it in here, all these elements we know that definitely belong in between these two indices. Then all we will do is simply make a recursive call to our algorithm. Let's call it quicksort. We will call quicksort to sort this part of the sequence. For this, we won't do anything specific. We will just make a function call. We will just call quicksort saying that sort for me the array part in between these two indices. We will make a second recursive call to sort the array part to the right of it in between these two indices. And finally, Once this is done, we don't have to do anything furthermore for the sorting operation, because now the whole thing, the whole array must be in sorted order, because pivot is in its correct position, left subarray is sorted, right subarray is sorted. Okay, this is the main algorithm. Let's first see the main algorithm itself. Again, we have a base case that is not explicitly mentioned in here, that we don't have an explicit code. Quicksort algorithm takes the input array A to be sorted, and this is the leftmost index of the part of the array that we want to sort. This is the rightmost index of the part of the array that we want to sort. If the array is indexed 1 through n, the first quicksort call will call left being equal to 1, right being equal to 1. Quicksort must make sure that the array, the part of the array A in between indices left and right are sorted in increasing order. Again, as I said before, we have a base case where we don't write any pseudocode for it, because the base case of quicksort will correspond to the smallest instance, and in the smallest instance we have a single element where left is equal to right. If left is equal to right, then the part of the array that we want to sort consists only a single element. If that is the case, we don't actually have to do anything to sort that part, because a single element by itself is already sorted. In general, this is the inductive part of our code. If left is smaller than right, we just write code that implements what we described in simple terms just a few minutes ago. We call our partition algorithm to say that partition the array A in between indices left and right such that those two properties are satisfied, such that the pivot element is in its correct position. By the way, we can assign any element to be the pivot inside the array A. For now, let's assume that we assign the leftmost element to be the pivot element. So from the partition algorithm, we want the array A in between indices left and right to be partitioned so that pivot is in its correct position in the array. All the elements to the left of it are smaller than or equal to it, and all the elements to the right of it are greater than or equal to it, are greater than it. Okay, let's assume that for now partition achieves this. That is, if this is the array, partition places the pivot, let's say this is the pivot, into its correct position. So this element is in its correct position, and it also makes sure that all the elements to the left of this element are smaller than or equal to it, all the elements to the right of it are greater than it. Then all we do is call quicksort to solve the problem, or to sort this smaller subsequence, say calling quicksort on the input array A in between indices. Note that left index doesn't change. Left index of the original array is the same as the left index of the subarray that we want to sort. Now the right index of the subarray that we want to sort, let's say that this is this index where the pivot element belongs to, turns out to be the middle index. Let's call it the middle index. Note that middle doesn't correspond to the exact middle of the array. So middle just tells us the index of the pivot element. Okay. If that's the case, then this subarray is in between indices left and middle minus 1. So all we do is call quicksort in between those two indices. Now we make a second call to our quicksort algorithm to do the sorting for the right subarray. Note that the right subarray is in between indices middle plus 1, because middle denotes the index of our pivot element, and right index. Okay, so once we make these two recursive calls, the left subarray will be sorted fine, right array will be sorted fine, and finally the pivot element will be at its correct position, will be at index denoted with middle. This means that the whole array after these three calls must be sorted. Is so far so good? Does everybody understand the general idea of the quicksort algorithm? Note that we haven't yet talked about the main part of the algorithm, which is this partition operation. We haven't yet talked about this, but assume that this partition call does what it is supposed to do, meaning that it basically divides and swaps the elements necessary in the array in such a way that the pivot element, which was the leftmost element in the original array, is in its correct position, which will be called the middle index, and all the elements to the left of it are smaller than or equal to it, and all the elements to the right of it are greater than it. As long as partition operation guarantees these two requirements, then these three lines of code should successfully sort the whole array. Is this clear? So this means that the most important part of our algorithm is this partition operation. Let's now try to see or try to design this partition algorithm. Okay, let's reiterate what the input and what the output of partition should be. Partition will take as input an array A and two indices, left and right. And what is this partition algorithm supposed to do? So this will be the general format of our inputs. Let's say that for now, leftmost index is given as the left index. So this is left, first element. This is given as the right index, right. The partition algorithm, it will first assume that this element is special. The leftmost element is special in the sense that pivot, it will assume that our special element pivot is this leftmost element. Pivot is a left. Assuming that pivot, the special element, is this element, the partition algorithm will do as many swaps as necessary on this array so that at the end it will have placed this pivot element into its correct position. Let's say this is let's say index 70, and let's say that pivot is the 70th smallest element, and it must place it into this position. Okay, so partition algorithm will place this element, this pivot element, into its correct position. Let's say that this correct position, the index of this correct position, let's call it middle. So it will place pivot into its correct position. Pivot will be here, and it will do as many assignments or swaps as necessary to make sure that everything to the left of the middle index is smaller than or equal to pivot. So everything in here is less than or equal to pivot. And everything to the right of the middle index is greater than the pivot. So this is what the partition algorithm should achieve. For the input array A, it should place pivot into its correct position, and also it should find out that position. But with this partition algorithm, we are at the same time finding out this middle index as well. Okay, basically finding out the index that the pivot element belongs to. But also we are making sure that every element to the left of that index is less than or equal to pivot. Every element to the right of that index is greater than pivot. Now, note that in our main quicksort algorithm, this partition algorithm is the main step because the rest is just recursive calls to again quicksort. This means that the running time of the quicksort algorithm depends only on the running time efficiency of the partition algorithm. If we make this one very efficient, then the quicksort algorithm will be very efficient. If the partition algorithm is not designed so carefully so that it's not efficient, then the overall quicksort algorithm will also not be efficient. Okay, so let's see how we can design the partition algorithm so that it will be as efficient as possible. Let's see the main idea first on a figure. Good. So let's say this is the input array A passed to the partition algorithm. This is the index left. So this is left. This is right initially. Basically, we need to partition this part of the array. Leftmost index is the pivot, so we first need to make a record of our pivot value. So pivot, we make an assignment saying that pivot is equal to A left. The main idea is the following. We keep two pointers, L and R. Basically, we will make sure that everything to the left of L is already processed. Everything to the left of L is already processed, and every element in here is smaller than or equal to pivot. Also, we will make sure that every element to the right of R is also processed, and every element in here is greater than the pivot. Let's say that this is true up until some execution step of the algorithm that this property is true. To the left of L, every element is fine, meaning that each one is smaller than or equal to pivot. To the right of R, each element is also fine, meaning that each element in here is greater than pivot. And let's just consider one single step of the algorithm. Let's say that this is where L is currently at. It is on this position, and R is currently on this array elements. To process these two elements, we will do the following. We will compare this element with the pivot. If this element is smaller than or equal to pivot, then it is fine. We can move on to the next element. If that next element is also less than or equal to pivot, then we can move on to the next, and so on. Okay. At the point where we stop, where the L index stops, we will just stop and wait. For the R index, we do the same thing. For the R pointer, we compare the element under the R pointer against the pivot. If it is greater, it is fine. We will move the R pointer towards left. And then again compare the element with the pivot. If it is greater, move the R pointer to the left because it is to the right of the R pointer. So the R pointer will stop at the array position where it finds out an element that is less than or equal to pivot. Okay. Note again the condition where L is stopped and R is stopped. L has stopped at the position such that the element under the L pointer is greater than pivot, meaning that that element actually belongs to the right of the array, and R pointer has stopped on the element that is less than or equal to pivot, meaning that that element actually belongs to the left of the array. Okay, since each one belongs to opposite sides, all we do is once this L pointer and R pointer has stopped, we swap their positions. We move AL, the array element under L pointer, into position R, and we move AR, the element under the R pointer, into the position L. Okay. Now once we do this, again, we have guaranteed that everything to the left of L is less than or equal to pivot. Everything to the right of R is greater than pivot. Now we can continue the same thing. Move the L pointer towards right until you find some element that is less than or equal to pivot. Move the R pointer in the opposite direction towards left until you find some element that is less than or equal to pivot, and swap those two. Again, do the same thing. Move the left pointer towards right, R pointer towards left until you stop and swap. So the main operation consists of moving the L pointer towards right until we find some element greater than pivot, and moving the R pointer towards left until we find some element that is less than or equal to pivot. We do a swap in between them, and then we continually do this. So continually move the left pointer towards right, R pointer towards left, swap, and continue doing this until when? Until these two pointers L and R meet each other. At that point where they exactly meet each other and pass each other, we know that that should be the position for our pivot, because up until now, throughout the execution of our algorithm, we have guaranteed that everything to the left of the L pointer is smaller than or equal to pivot, and everything to the right of the R pointer is greater than the pivot, which means that at the position where L and R pointers meet, then everything is in its correct order. Everything to the left is fine, everything to the right is fine, and the position that they meet is actually the position where the pivot element belongs to. So after this short explanation on the figure, let's see the pseudocode itself. We first assign the leftmost element as the pivot. As we said before, this will be the pivot. We initialize our L pointer first as the leftmost position and our R pointer first as the rightmost position. Inside, what we do is, as we said before, we will keep on doing two operations, basically moving L towards right and R towards left, and doing a swap. These two operations we will keep on repeating until those two pointers meet each other. Basically, as long as L is to the left of R, as long as L is smaller than R, we will keep on repeating those two operations. Move L towards right, move R towards left, and swap. Let's see the details of those two operations. L pointer, we check at every L value if the current value under the L pointer is less than or equal to pivot, we increment the L pointer, meaning that we move the L pointer to the right by 1. We keep on doing this until AL, the element under the L pointer, is greater than the pivot. Of course, we should also make sure that L pointer doesn't exceed the given limits of the array, the rightmost position of the original array. And the R pointer, as long as the element under the R pointer is greater than the pivot, we keep on decrementing R, meaning that we move R pointer towards left. Until when? Until the element under the R pointer is less than or equal to pivot. At this point, the element under the L pointer is greater than pivot, meaning that it belongs to the right of the array. Is smaller than or equal to pivot, meaning that it belongs to the left of the array. If that is the case, we simply swap those two elements. We swap AL and AR. But of course, we need to check that L and R are still in the expected positions. L should always be to the left of R. Okay. Now, remember, we continually do these two operations, moving L and R, and then doing the swap. We continually do this until those two positions, those two pointers, L and R, meet and pass each other. At that point, we know that the R index is where our pivot element belongs to. The middle index is actually R. This is where the meeting point of those two pointers is the index where the pivot element belongs to. So we do a final swap operation where we place the pivot element, which was at A left, into its correct position. So we swap A left with A middle because A left is the pivot and its correct position is at the middle index. You should be able to see that this algorithm guarantees what we required, that it places the pivot element into its correct position, which is the middle index, and everything to the left of it is less than or equal to it, everything to the right of it is greater than it. Because note that when we move pointers L and R towards each other, we make sure that we swap all the elements necessary. So L will stop at a position at an element that is greater than pivot. R will stop at an element that is less than or equal to it, and then we will swap them. We will put them into correct subarrays, and then we will continue. At the moment that L and R meet, we have made sure that everything to the left of L pointer is smaller than or equal to pivot, and everything to the right is greater than pivot. So, is the partition algorithm clear? Any questions about the partition algorithm? So Emir is asking why we have swapped AL and AR. You mean at this position, we first check if L is less than R, then swap AL AR. You're asking about this line of code. Okay, so as I said before, so let's actually see this on an example. Okay, Emir. If we see the operations of the partition algorithm on an example, it will make it clearer. So let's take a look at this example. This is our input array. Okay. As we said, let's assign the leftmost element as our pivot, which is 6. Initially, this is left, the leftmost pointer, and this is right. Initially, the L pointer will start here. The L pointer is initially equal to left, and the R pointer initially is equal to right. So the R pointer points to here initially. Okay, now we go inside the while loop. L is less than R. Okay, so we will execute whatever is inside the while loop. Inside the while loop, for the first part, we will keep on moving the L pointer towards right until we find an element that is greater than pivot. So this L is initially here. 6 is less than or equal to 6, so will move towards right. 2 is less than or equal to pivot, so will move towards right. At this point, 8 is greater than the pivot, so L pointer will stop here. So this initial while loop will finish its iterations. We are at this point and L has stopped on this element because this element is greater than pivot. Now for the other side, for R, we initially start R being equal to right. 14 is greater than 6, greater than pivot, so R will move to the left. 15 is greater than pivot, so will move to the left. 11 is greater than the pivot, so will move to the left. Finally, the R pointer will stop on this element, on 4, because 4 is less than or equal to pivot. This is what this second while loop tells us to do. Move R to the left as long as AR is greater than pivot. Stop when the element under R pointer is less than or equal to pivot. Now at this point, L has stopped on 8, R has stopped on 4. We know that this element belongs to the right of the array because every element at the end that is greater than pivot, that is greater than 8, should go towards right. The opposite is true for this element, 4. We know that it is less than or equal to pivot and it belongs to the left side of the array. If this is the case, we simply swap them. We simply swap AL and AR. So 8 is now here, 4 is now where 8 was supposed to be. Okay? Now note that our L is pointing to here, R is pointing to here. At this point, we have guaranteed that everything to the left of L is smaller than or equal to pivot. And also we have guaranteed that everything to the right of R is greater than pivot. And our external while loop, the while loop outside, tells us to keep on doing these two operations as long as those 2 pointers have not met. So currently this is L, this is R, they haven't met yet, so we repeat the same operation. Okay, 4 is already smaller than or equal to pivot, so we move on to next. For L, we move on to next the element 5. 5 is less than or equal to pivot, so we move on to the next element, which is 10. At this point, L pointer stops because 10 is greater than pivot, greater than 6. For the R pointer, currently it is on 8. 8 is greater than pivot. 13, it moves left. It sees 13 and 13 is greater than pivot. It moves left. Now it finds out that the element underneath 3 is less than or equal to pivot, so it will stop. The L pointer stops on 10. The R pointer stops on 3. And we now simply swap them. Okay, so 3 goes into the position where 10 was before, and 10 goes to the position where 3 was before. Okay, this is 3 in the position of 10, this is 10 in the position of 3, and we go back. We have done the swap. We go back to the outer while loop, which tells us if they haven't met these 2 pointers L and R, keep on doing the same operation. So we will do the same operation. 3 is smaller than or equal to pivot. L pointer moves to the right by 1. Now 9 is under pointer L, and 9 is greater than pivot. So L stops here. For R, it starts on 10. 10 is greater than pivot. Next, it moves left. 7 is greater than pivot. Next, it moves left. 15 is greater than pivot. Next, it moves left, and it stops on 1 because 1 is less than or equal to pivot. Again, at the position that these 2 pointers stop, we swap those 2 elements. We swap 9 and 1. So 1 is now where 9 was before, and 9 is where 1 was before. And keep on doing the same thing. This was L. So L, underneath L we have 1. So it moves to the left. Now underneath L we have 12, which is greater than pivot. So L will stop on this element. Remember, R in the previous step was on 9. 9 is greater than 6, greater than pivot, so it will move left. 12 is greater than pivot, so it move left. And R finally will stop on 1 because 1 is less than or equal to pivot. So this is the position at the end where R and L have stopped. Okay, so since they have stopped, so we now quit the whole while loop because L now is not smaller than R. These 2 pointers have met and passed each other. Let's look at the figure now. You should be able to see that now everything that lies to the left of R is smaller than or equal to our pivot value, which was 6. And everything to the right of our pivot of our R index is greater than the pivot value. Finally, the only thing that remains us to do is place the pivot element into its correct position. To do this, we simply, as the pseudocode tells us, we simply swap A left and A middle at the end. So A middle we know is this position. Okay, we simply swap at the end the values 6 and 1. Let's look at the final figure. 6 was our pivot value. It is in its correct position. This is the position where 6 belongs to exactly in the whole array. Every element to the left of it is smaller than or equal to 6. Every element to the right of it is greater than 6. Notice that we don't expect anything else regarding this left subarray and right subarray. We don't expect them to be sorted. As long as all the elements in here are smaller than or equal to pivot and all the elements in the right subarray are greater than the pivot, we are fine. Because we will simply call quicksort on the small array, and quicksort itself, that recursive call, will handle everything by itself. It will sort this part into 1, 2, 3, 4, 5. And we will call quicksort on this subarray and not worry about anything else. The recursive quicksort call will simply sort this part of the array in its sorted order. At the end, we will have the whole array in sorted order. Is the example clear? Emir, is it clear why we swap AL and AR? Any other questions? Any questions regarding the pseudocode or regarding the example that we went over? Is the quicksort algorithm clear? Okay, now that Now I'm assuming that you have understood the quicksort algorithm, and you can see regarding the correctness of the quicksort algorithm that it is supposed to correctly sort a given input array A, and I also assume that you have understood the partition algorithm itself. Let's give a break of 5 minutes. Let's give it for 5 minutes so that we can try to finish a bit earlier. And after 5 minutes, we can now start analyzing the running time of the quicksort algorithm. Okay, so let's right now it's almost 2:50. Let's stop at this point and we will meet again at 2:55, 5 minutes later. Okay.